Yeah, good evening. Yeah, good evening, everyone. My voice is audible.
Good evening, sir. Yes, your voice is audible, sir.
My, okay, thank you, ma'am. Okay, session will start within few minutes. We are waiting for the some more participations. Balu sir, Balu sir. సార్ లైన్లో ఉన్నారా సార్ మీరు? ఓకే సార్. స్టార్ట్ చేద్దామని ఇంకా జాయిన్ అయిపోయారు సార్. మీరు జాయిన్ అవ్వచ్చు సార్ ఇంకా. ఓకే సార్, ఓకే సార్. Yeah, good evening, everyone. We start this session. First of all, good evening to everyone. Thank you for participation in the 1 month online training program on digital system design using Verilog HDL. This program is associated with the Institute of Engineers, Kadapa Local Center. Okay. First of all, Ekalavya group of technologies. Okay. Please all of you mute yourself. Okay. If we have any queries, we will ask the end of this session. Okay. Next. Ekalavya, first of all, about the Ekalavya group of technologies. Ekalavya group of technologies established in the year of 2019 with a prime motto of imparting quality training in engineering. For a small institution with just a handful of the students in the year of 2019 in Tirupati, the institute has grown by leaps, bounded and established itself one of the leading institutions in Andhra Pradesh. Okay. Next. Ekalavya Group of Technologies provide the innovative engineering skill development solutions for engineering students and who are interested to learn advanced technologies in various domains like VLSI, embedded, artificial intelligence, IoT, Python, and Java, etc. And Ekalavya Group of Technologies offers the 6 weeks and 6 months industrial training or internship for the BTech and Polytechnic students of ECE, EEE, TME, IT, and etc. And our experienced trainers impact practical knowledge, share their experience, and prepare the students for the technical world. And all these activities are done in the only training period session. And students also get the work in the live projects also. Next, we assistance the enhanced to job placement days, also giving the support to students feel feel more comfortable and more confidence, exhibit problem solving skills, and gain industry exposure during the training period. And industry training helps the students to learn new technologies, stay them updated with the marketing demand, and making them making them aware of the new development and discoveries and develop skills and competitive and required to the become employable. An A-Club group of technologies can handle the research and academic projects related to various technologies for different disciplines like UG and PG. An A-Club group of technologies are implementing and developing innovation projects and engineering by providing the complete explanation information. Next, today our research person is Dr. N. Baldasgiri Garu. He has more than 4 years industrial experience and more than 9 years academic experience, and he is published more than 4 patent journals and four books. And he published the 12 SCI Index Scopus journals. And he is a good well-wisher of the ECLO group of technologies. And thank you for participating. Dear Baldasiri sir.
Hello, Suresh. Yes, Suresh. Yeah.
Please address yourself.
Hello, Suresh. Is my voice audible?
Sir, some noise is there, sir.
Yeah. Now is it okay? Yeah. So my name is Dr. N. Balarastagiri. So I welcome you to 1 month online training program on digital system design using Verilog HDL on behalf of Ekalavya group of technologies. So I have been associated with Ekalavya group of technologies for quite some time. So and I am happy to act as one of the resource person for this workshop. So today, let me share you the various design flows that are associated with the VLSI. So from tomorrow onwards, so we'll be starting the regular classes of Verilog. Okay. So today, let me give you a brief description of VLSI and what are the various flows that are associated with it. Okay. Nowadays, the term VLSI, that is very large scale integration, has become a household acronym. The people who doesn't know the technology as well as the people who knows the technology will be talking about the ICs, will be talking about the VLSI, everything. Okay, so the VLSI is the process of fabricating an integrated circuit by combining the billions of transistors on a single chip. Okay, so actually these silicon chips are made from the sand. So as you well aware that, so these are heat. The sand is taken and these are heated at 1400 degrees centigrade. So from there you get the liquid form of the sand, and this liquid form of the sand is made into circular plates. So after the perfect etching of these circular plates, so you will be getting the silicon wafers. So on these silicon wafers, these ICs will be fabricated. Okay, so the way to VLSI had begun in the early 1970s when communication and semiconductor technologies were being developed. The evaluation of VLSI technology was not a task, so it is not done in a year or so. So many years have been went past in developing the VLSI technology. The first technology in the IC fabrication was termed as small scale integration. So in the small scale integration, so 0 to 10 number of transistors were fabricated on the silicon wafer. So after the small scale integration, so next technology is medium scale integration. So in the medium scale integration, 0 to 100 number of transistors were fabricated on the single silicon wafer. So after the MSI technology, the next technology to emerge is LSI, that is large scale integration. So in this large scale integration, so up to 1000 number of transistors were fabricated on the single silicon wafer. So before the evaluation of VLSI technology, so most ICs had a small number of transistors or limited number of functions they can perform. But after the ALSI, so next to emerging technology is VLSI, so which is known as very large scale integration. So up to 10,000 number of transistors were fabricated on the single silicon wafer. Okay, so next later we will be talking about so in the few textbooks or websites we'll be talking about the ULSI, that is ultra large scale integration, and the GSI gain scale integration, everything. But from the point of VLSI up to now, the every technology has been termed as VLSI only. So even though you may call it a ultra scale integration or gain scale integration, so together all these terms are referred to as VLSI. So if you take the VLSI, the most important part of the VLSI technology is the Moore's law. So where the number of transistors on the silicon wafer will be doubled for every 18 months. So but nowadays we have went past that Moore's law also. So nowadays for every 18 months, so the transistors are not doubled. So they are multiplied by some number. So they are multiplied 10, 20s. So everything. So in the last few years, if you take, so due to the advancement in the system design applications and VLSI technology, so there is a tremendous growth in the field of VLSI industry. So with the help of VLSI, very large scale integration designs, a good number of IC applications of integrated circuits in high performance controls, computing, image and video processing, consumer electronics and telecommunications has been rising at a very good pace. The current cutting edge technologies such as cellular communications, the low bit rate video with high resolution provide the end users a tremendous amount of applications. And moreover, so due to the use of portable and low power applications, so VLSI has made an impact in the consumer electronics. Okay, so the VLSI design flow is further discussed in the given figure. So it is the VLSI design flow. So most of you might have seen this figure. So it is not a new. So but so let us see the VLSI design flow. So these are the different levels of steps so associated in the VLSI design flow. So these are design specifications, schematic capture, create symbol, simulation, layout, design rule check, extraction, layout versus schematic, and post layout simulation. So these are the various design VLSI design flow steps that are associated. So firstly is nothing but the specifications. Okay, so what do the specifications do? The specifications describe the conceptuality, the functionality of the design. So what is the interface required and what is the architectural circuit of the IC to be designed? So everything comes under the specifications. Okay, so for example, I want to design a ripple carry adder. So in order to design a ripple carry adder, so first the specifications I need to know. So what is the ripple carry adder? So why we are going for the ripple carry adder? So after knowing that, so how many bit ripple carry adder we are going to design? So whether you want to design a 4-bit ripple carry adder or 5-bit ripple carry adder or 6-bit ripple carry adder. So once you confine with the number of bits of ripple carry adder, so next you need to know what is the type of full adder we have to use it. So whether you can directly use the full adder, so or we can design the full adder by using the 2 half adders. So like this, so we have to write everything in the specifications. Okay, so specification is nothing but the description of your design, so description of your project. So once you go into the project, the whole description of your project, so the algorithm, the flow chart, and moreover here also you have to make sure that so whether your design is a white box design or black box design or gray box design. Okay, so all these specifications should be amended here, and moreover you have to make the decision how much time you require in order to implement this project. Okay, so if you want, in order to implement this project, how many employees you should require, so what are the teams and who is the team leader. Okay, and next what are the tools available with you? So is these EDA tools will help you to design the work or not? Okay, so if not, so what are the tools you have to purchase? That is the EDA tools you have to purchase. What not? Everything in order to from the idea to the implementation, so everything has to be specified. So this comes under the specifications. And here the most important part when you go for the specifications is the designing. So here, as I told you, there are three types of designing. So one is white box design, black box design, and the gray box design. So black box design means so depending upon the user interface or depending upon the project, you can go for any type of the design. Okay, so let me say what are these designs here. So black box design means, so the user or the person to whom you sell your project, okay, so he doesn't know what is there inside the design. Okay, so what are the connections, everything he doesn't know. So he is made available to know, so what are the inputs and what are the outputs of your design. Okay, so for example, if you take this full adder as a black box design means, so the person to whom you sell your project will know, so there are only three inputs, so ABC are the three inputs and someone carry are the outputs. Okay, so he doesn't know how you have designed your design. Okay, so what are the connections, whether you have followed which model, if you have created the schematic chart, if you have created the uh, coding to the Verilog. So the designer only knows that. So other members will not know that. So that is known as the black box design. So the next one is the white box designing. So white box designing means, so the designer as well as the person with whom you are discussing, so he will know, so what are there inside the design, so what are the connections. Okay, so how you have designed, so what everything, so everything will be known to the designer as well as to the customer. So next one is gray box designing. So gray box designing means, so only some part of the design will be made available to the customer, and other parts of the design will be taken as the black box designing. So it is nothing but the gray box. So gray box is the combination of white box as well as the black box. Okay, so this is about the specifications here. So in one word, if you can say that design specification means, so they describe the conceptuality, the functionality of the design, the interface required, and the architectural circuit of the IC that to be designed. So these are all discussed in the specifications. So the next step in the specification is, normally here you can go for two types here. Okay, so one is schematic capture or RTL description. Okay, so the next step I have taken is the schematic capture. So here two types will be there. So one is the RTL description, so that which is nothing but the coding of your design or the schematic of the design. Okay, so if you are going for the pure digital point of view, so digital circuit point of view, so normally you go for the coding, HDL coding. So that HDL coding may be the VHDL coding or the Verilog coding. For suppose if you are going for the analog circuit means, so here you have to draft the schematic. That is, you have to draft the schematic. So for this schematic, you have to analyze the performance. Okay, so if you are going for the analog means, so the next step will be the schematic capture, or if you are going for the digital point of view means, here we have to go for the RTL description. So this RTL description will be done using VHDL or Verilog. So these are the hardware description languages. So apart from the hardware description languages, we have the hardware verification languages by like System C and System Verilog. So by using this also you can create your designs. Okay, so normally people will be going for the Verilog or System Verilog depending upon the employees available and the language which is known to them. Okay, so let us see the HDL language. The HDL is nothing but the hardware description language. As I told you, two types of HDLs. One is VHDL and Verilog HDL. So VHDL stands for very high speed integrated circuit hardware description language. So which we can see in the later also the differences. So and the Verilog HDL stands for verification logic HDL. This VHDL has been developed from the Pascal language. So whereas Verilog has been developed from the C language. The main syntaxes, everything are based from the C language in Verilog, but the VHDL has been developed from the Pascal language. Okay, so and the VHDL is not a case sensitive, so whereas Verilog HDL is a case sensitive language. So in the Verilog HDL we have to use all the words in the lower case, but in case of VHDL you can use either uppercase or lower case. In Verilog HDL we have to remember that the everything has to be there in the lower case. Okay, so next, so after that, okay, so next thing is in case of VHDL. So in case of VHDL, we have the different entities. So in case of VHDL, so we have to define the libraries separately. After that, in order to design your input and output blocks, we have to go for the entity declaration, and the logic will be written in the architecture. But whereas in case of Verilog HDL, so everything will be written within a module. Okay, so and moreover, VHDL is mainly used in the defense applications because of its security, and Verilog is used in the consumer applications. Okay, so if you take the VHDL language, the syntaxes of VHDL languages are quite lengthy, and in case of VHDL, in case of Verilog, as Verilog is mainly developed from the C languages, the syntaxes are very short, and it is the one of the reason also we are using the Verilog HDL in the consumer electronics. Okay, so after writing the Verilog or VHDL program, so the next thing is we have to go for the simulation here. Okay, so next we have to go for the simulation. So in here there is a one more step. So after the schematic capture is done, so we have to go for the create symbol. So if you are going for the analog design, so if you are going for the analog design, what happens is that for example, I want to design a ripple carry adder, which I have told you. So in order to draw a 4-bit full adder in the same circuits and the same schematic page, it is very difficult. Why? Because so we have to start from the scratch. So first we have to construct the full adder. So in order to construct the full adder, if you are constructing the full adder, and from the full adders, if you are drawing the ripple carry adder, means the circuit becomes very clumsy. Okay, so that is the reason why what they will do is that first we will design a full adder, and we will convert that full adder into a symbol, and that symbol will be taken. Okay, so and that symbol will be taken in the schematic. So you will take the required number of full adders. Okay, so it is in order to make the design process easy, so we are creating the symbols. Okay, so after this, the next one is simulation here. So simulation, so what is meant by simulation means giving the inputs and finding whether you are getting the output or not. So there is a very deep discussion has been made so between simulation and functional verification. So there is a difference also between the simulation and functional verification. So simulation means if you give the inputs, you should get the outputs. So whether that inputs may be right or wrong, you can say that the circuit is simulated. The circuit is simulated when if you give the inputs, you are getting the outputs. The circuit is simulated, but here we are not talking about the functionality. So functional verification means, so whatever the circuit or whatever the code you have written, so we have to simulate that, and we have to make sure that so by giving the set of input patterns, so we are getting the correct outputs or not. So this is known as the functional verification. The functional verification, if you are getting the correct outputs for the given inputs, so then you can say that your code is functionally verified. Otherwise, your code is not functionally verified. So I think all of you know now the simulation difference between simulation and functional verification. So functional verification means until unless you get your functionality of your circuit correct, you cannot say that your circuit or code is functionally verified. So simulation means give your inputs and you will get the output. That output may be correct or wrong. So it is known as the simulation. Okay. Once simulation is done, Okay, so the next one is layout. Okay, so before going to the layout here, in case of digital circuit, so what happens is that the functional description will be converted into a gate level netlist with the help of logic synthesis. Sorry. Hello.
Sir, please, your screen not visible, sir. Please, once again, resume your screen, sir. Resume your screen, sir.
One minute, Suresh. Yeah, it is full raining here, so that
Okay, sir.
problem. Network problem is there.
Okay, sir.
Yeah, is it visible, sir?
Yeah, no, visible, sir.
Okay, sir. So before going for the layout, Suresh, resound.
Sir?
Hello.
Yes, sir. Tell me, sir.
Resound.
Resound, sir. మీ సైడ్ నుంచి resound వస్తుంది, sir.
ఆఫ్ చేస్తాం. ఇప్పుడు సురేష్.
No, okay, sir.
Okay. So screen visible అవుతుందా?
No, visible, sir.
Yeah.
Okay, sir.
So actually, from the simulation, so directly you cannot, if it is the analog layout means you can go to the layout, but you are talking about the digital means the whatever the after the simulation, so whatever the functional description or the RTL description is there, so that is converted into a gate level netlist. Okay, so which is known as the logic synthesis. Okay, so logic synthesis means conversion of HDL program into the gate level netlist. So here the netlist means it is the combination of logic gates and their logic connections. So netlist will show you the internal connection of your design in terms of logic gates and their connections. Okay. So this is done. So why the generated netlist, as I told you, so it consists of logic gates and their internal connections, and it is mainly used for achieving the area and power specification. Okay, the next one is the layout here. So the layout is nothing but the geometrical representation of your design. Okay, so this plays a crucial role. So whatever the circuit you have done, so we are going for the geometrical representation of your circuit. So in the most of you might have aware of the stick diagrams also. Okay, so the basic difference between the stick diagrams and the layouts is that, so stick diagrams are the nothing but the graphical representation of your circuit. So layout is the geometrical representation of our circuit. So why we are using the stick diagrams means, so stick diagrams is for our perception. Okay, so they are not anything to do with the technology, but for the better understanding of the users or better understanding of the designers in the what way, what materials we have to use or what layers we have to use it for the designing of layouts, stick diagrams will be used. So otherwise the layout is the only thing, so that will play a crucial role in the VLSI design flow. Okay, so as I told you, so layout means nothing but the geometrical representation of our circuit. Okay, so whatever the netlist we have created, so if it is a schematic netlist, if it is from the digital or from the analog, so whatever the netlist is generated, so for this netlist we are going to implement the physical layout. Okay, So what does the layout give means? So it will give the information about the technology what you are using. Okay. So if you see, so there are different technologies. So that may be CMOS 45 nanometer technology, or CMOS 22 nanometer technology, or CMOS 65 nanometer technology. So all the information so will be given in the layout.
Sir,
Suresh.
sir, sir. Sir, no, sir, this is Likit. Sir, what is CMOS? CMOS
Complementary
means?
metal oxide semiconductor. Hello.
Okay, sir.
So actually, so I will tell you that also. So at present, so we are using the FinFET technology. Okay. So it is a double gate FinFET tech. Now we are using the FinFET technology. So what is meant by the technology means the technology is nothing but the size of the transistor in the design. So CMOS 45 nanometer technology means that the type of transistor we are using is CMOS transistors. Okay, so we are using the CMOS transistors, and 45 nanometer technology means it is nothing but the channel length. The channel length of the transistor is 45 nanometers. So it is nothing but the technology. So whatever the channel length we are using, so this refers to the technology. So nowadays what you say is that the technology is increasing. So technology is increasing means nothing but the size of the transistor is decreasing. So why we are getting the compact devices and the portable devices means we are able to fabricate more number of devices on the silicon wafer. So that means so more in the given area, so we are able to incorporate more number of transistors. So that is the reason. Okay, so how we are able to incorporate more number of transistors in the given area means the size of the transistor has been reduced. Okay, so as I told you, so now we are running at 5 nanometer, and maybe that 5 nanometer technology, in fact, technology may be into the market next year, I think so. And so after designing the layout, the next one is design rule check. Okay, so design rule check. So in the layout, there will be different layers. Okay, so in order to, if you take a transistor, in order to specify the inputs and outputs of the design, so you have to refer to one type of layer, that is the polysilicon layer. So if you want to denote the VDD and the ground, that is the power rails, so we have to go for the metal. So metal one. So similarly, if you are going for multiple layers means you have to refer to the various layers. So metal 1, metal 2, metal 3, metal 4, like that. Okay. And in order to connect two different material means we have to go for the connection of the two different materials by using the vias. Okay, so again depending upon the feature length. Okay, so depending upon the feature length, so whatever may be the feature length, 45 nanometer or 16 or 65 nanometer, so these rules of drawing the layout, the particular design will vary. Hello.
Sir, it seems to be quite fast, sir, what you are explaining. Of course,
Okay.
yeah, we are getting what you are saying and we are well understanding, but what you are
Okay.
saying is quite very fast, sir.
Okay. So I will go slow. So, when you are designing the layout, so there will be different layers in the layout. So it is not the simple task to draw the layout. So we have to follow some rules. Okay. So like lambda rules. Okay. So this lambda is nothing but, so lambda is equal to feature size by 2. Okay. So feature size is nothing but the technology what you are using. So if you are taking the lambda rules, the minimum width of the power rails, that is the VDD and ground power rails, is 3 lambda. So the minimum width of polysilicon is 2 lambda. So like that, there are different rules to draw the layout. Okay. In the design rule check, which is also known as DRC, what we will do is whether the intended layout is following the specified rules or not. So the specified layout rules are followed by the layout you designed or not. So that the design rule check will verify. So what does the design rule check will do? So just it will verify whether we have drawn the layout by using the specific layout design rules or not. Okay, so if you are not following the specific design rule check, then your layout is not valid. Again, we have to go back to the layout. We have to make sure that the intended design rules we have followed. Okay, so once the DRC is correct, so in the DRC what you are doing, so here we are checking only whether the layout is following the rules or not, but here we are not checking the functionality of your layout. Okay, so in the DRC we are only verifying the design rules of your layout, whether they are correct or not, but we are not going for the functionality. Okay, so after the design rule check, next we have to go for the, so before the extraction, so sometimes we go for the LVS. So before we have to go for the layout versus schematic check. So layout versus schematic check is also known as LVS. Okay, so it is also known as LVS. So here what you do is, for the layout what we have drawn, for the geometric connections of your circuit, you cannot verify the functionality. So if you want to verify the functionality, you have to simulate that, or for example, if it is analog circuit, means you have to give the input voltages and the voltages to the power rails, and we have to verify the output. So but you cannot verify that for the layout. Okay, so in order to know whether your layout is functionally correct or not, so what you do is that you will generate the netlist for your layout, as well as, so after simulating your circuit or after functionally verifying your design, you will also generate a netlist. Here you will compare the netlist of your layout as well as the netlist of your schematic. Okay, so once these two are correct, so if these two are same, then you can say that the functionality of your layout as well as the functionality of the schematic or the functionality of the design which you have taken is correct. So then you can say that the layout is having the same functionality of your schematic, then you can proceed. If the layout is wrong means, the layout is having different functionality and the schematic is having different functionality. That is the meaning. So until unless the LVS is correct, you cannot proceed further. If the LVS is correct only, you can proceed further. So once the LVS is correct, so the next we have to go for the extraction. That is, we have to go for the parasitic extraction. So what is meant by the parasitic extraction means, so while you are drafting your layout, so some unwanted capacitance and unwanted resistance might have been crept into your layout. So this we have to extract the unwanted capacitance and unwanted resistance, and we have to estimate the behavior of the circuit if there are these unwanted capacitance and unwanted resistance in your circuit. So all this analysis comes under the parasitic extraction. So after that, you may go for the after extracting the parasitic, so we are going for the post layout simulation. So this post layout simulation, we will compare it with the normal simulation. Okay, what we have done. So functionality which should be the same, equality should be there in the functionality. If the equality is different means, again we have to go for the starting. So from the schematic capture, we have to start. Okay, so this is after getting the post layout simulation correct. So next we will getting the GDS2 file. So this GDS2 file will be sent to the foundries. Okay, so the total design process will not be given to the foundries. So after the designing process, whatever the GDS2 file you get, that is graphical data sheet interchange information file. So this file will be given to the foundries. So there are different foundries in the world like TSMC, AMI. Okay, so the file will be given to that. So by using that file only, so they will fabricate your IC. So there is no need of giving the total design. So from the design specifications to the layout, everything. So that is not required to give to the foundries. So only the GDS2 file will be given to the foundries. Okay. So this is about the VLSI design flow. Okay, so let us see the major designs in the design of IC. Okay, so the major designs in the design of IC here. ASIC design flow and FPGA design flow. So I think all of you know the basic difference between the ASIC and FPGA. Okay, so ASIC means application specific integrated circuit. ASIC stands for application specific integrated circuit, and FPGA stands for field programmable gate array. Once again, I repeat you the acronyms. So ASIC stands for application specific integrated circuit, and whereas FPGA stands for field programmable gate array. Now, let me say what are the differences between these two. Okay, so if you want to directly go for the designing of an IC, okay, so if you want to go for the directly for the designing of an IC, for example, if I want to go for the design of a digital IC, so after directly if I invest some money in the designing of the IC, and if this after getting the that is the IC hardware, and this hardware is not working properly, means what happens? The total investment so is waste. Okay, so in order to, for example, in order to design a simple AND gate IC also, it takes some lakhs of money. Okay, so when the why? Because if you are designing some 10 lakhs of ICs or single IC, so the initial cost like engine needs, the softwares which you want to purchase, everything will be the same. So but the only variation you will be getting in the fabrication cost. Okay, so if you are fabricating a more number of ICs for the same technology or for the same design, means the cost of the hardware gets reduced. Otherwise the cost will be very high. So if you not properly working on the designing, and if you develop an IC and this hardware might not work properly, means the total cost invested will be waste. So in order to see that, so what you will do is that, so the digital designing mostly will be done in the FPGA. So FPGA is field programmable gate array. So where it consists of where it is a reconfigurable IC. Okay, so FPGA is a reconfigurable IC. So here there will be some cells here. So in this, which are known as the LUTs. So whatever the design we have done, so that design can be incorporated into this FPGA. So after incorporating the design into the FPGA, so the FPGA starts acting as the IC. For example, I have designed the full adder IC and I have implemented the full adder program into the FPGA, means the FPGA IC starts to work as adder IC. So after that, what I can do, again reconfigure that. Okay, so now I will design a decoder and I will implement that decoder into the FPGA. So then FPGA IC will act as a decoder IC. So like this, so FPGA can be reconfigured for any application. So whereas ASIC is application specific, the name itself you can see it is application specific here. So for example, if you want to design an adder IC, means so the ICs which you are digital ICs which you see in your lab are the examples of this ASIC. So they are only specified for that application. So they cannot be used for other applications. So adder IC means it is only used for the adder. You cannot use adder IC as a subtractor, or you cannot use adder IC as a decoder or multiplexer. Okay, so it is only for specific application, but FPGA is the reconfigurable. Okay, so yeah, before going for the implementation of the ASIC, so first thing what you will do is that for the digital ICs, so we will implement the functionality of your program on the FPGA IC, whether to make sure that the compatibility of your design will be working well on the FPGA or not. So if it is working well, means then you go for the ASIC designing. Okay, so that is for the application specific IC. So if you see here, the first one will be nothing but the design entry here. So design entry means writing the VHDL or Verilog HDL program. So depending upon the expertise what you have, you can write the VHDL, or you can write the Verilog programming, or else you can write the system Verilog. our system, writing the program. Once the functionality of our design is properly done, so the next one is logic synthesis. So in the logic synthesis means why we want to go for logic synthesis. Why? Because the whatever the HDL program will be written will be the high level language. So that part of the language will not be understood by the equipment what you are using. So we have to convert your program into the target understandable language. So whatever the target you are using, okay, for example, it is the ASIC means, so we have to convert your HDL program into the technology based language. So whatever from using the 45 nanometer technology means, so I have to convert my HDL program into that 45 nanometer technology based language. So if I am using the FPGA means, I want to convert my HDL program into the FPGA understandable language. So that is nothing but the logic synthesis. So logic synthesis means conversion of HDL program into a netlist. So you can say that logic synthesis means conversion of your HDL program into the netlist, or else you can say that conversion of your HDL program into the target understandable language, okay, or else you can say that conversion of your HDL program into the target primitives, okay. So what is meant by netlist means, so netlist is nothing but the interconnection of the logic gates. So what in the design you may have used different logic gates. The interconnection of these logic gates is defined in the logic synthesis, that is in the netlist, okay. So after this, so after the logic synthesis, so for example, if the designs what you are designing are very bigger, okay, so whatever the designings you are there, so these are very bigger, okay, so then we have to convert them, or we have to divide them into equal pieces. So that is known as the system partitioning. So whatever the designing we are taking, so this designing should be divided into the equal pieces, okay, equal pieces. So that is known as the system partitioning. So system partitioning means, so nothing but the designing of your circuit into, that is dividing of your larger system into ASIC sized pieces. So it is nothing known as the system partitioning. So the next one is, so after the system partitioning, sometimes you go for the pre-layout simulation. So in the pre-layout simulation, so before the layout is prepared, so we will be doing the functional verification of your design. So whether we are meeting the functionality of the circuit or not. So after that, the next one is floor planning, okay. So you can see here, so there is a chip there, okay. So floor planning is nothing but how you can arrange the logic blocks on the netlist, okay, how you can arrange. So suppose, for example, I want to design a IC, I want to design a 4-bit triple carry adder IC, okay. So now in the given area, so in the given area, how can I arrange the full adders? So here in the triple carry adders, the logic blocks are nothing but the full adders. That is the major level blocks are nothing but the full adders. In the triple carry adder, in the 4-bit triple carry adder, the major blocks are full adders here. So how you can locate or arrange the logic blocks of the netlist are known as the floor planning. So the placing of logic blocks on the given IC are known as the floor planning. So next one is placement, okay. So placement means, so placement is used for selecting or deciding the position of logic cells in the logic blocks, okay. So if you are taking the logic blocks, inside the logic blocks there will be logic cells, okay. For example, if you take a full adder IC, sorry, in the full adder logic block, again you have the XOR gates, okay, we have the AND gates, we have the OR gates. So gates placement, that is known as the placement, okay. So floor planning means arranging or locating the logic blocks of the netlist, whereas the placement is deciding the locations of the logic cells inside a logic blocks. And next one is routing. Okay, so routing is defined as the process of making connections between the cells and the blocks. So whatever the logic blocks and whatever the logic cells are present, so the interconnection these logic blocks and logic cells is known as the routing. So giving connections between them. Okay, so there are two types of routing. One is global routing and second one is local routing. So global routing means in the global routing, just we will make a plan how to give the connections, but the connections will not be taken place. That means the routing will not be taken place. The actual routing takes place only in case of the local routing. So the actual connections will be done only in the local routing. Okay. So in order to simplify that, so let me tell you, for example, if you take an engineering college as a IC, okay, if you take an engineering college and IC, so first what you will do, so you will divide the area into different parts. So that is known as the smart system partitioning. So next floor planning means, so first you will place ECE block at some point. Triple block we will place next. So CSC block. So next administrative office. Okay, next placement office. So these are the different logic blocks. So placing of these logic blocks is called as floor planning. Next placement means, so if you take the ECE department, so in the ECE department there will be HOD room, so there will be different laboratories, there will be classrooms. So these are the logic cells inside the logic body. Okay, so these are nothing, placing of these classrooms, placing of these laboratories and HOD room, staff rooms. So this is nothing but the placement. Okay, I think you understand now. So floor planning means in a college, placing of different departments is known as the floor planning. So placement means, so in each department, placing of the laboratories, location of the laboratories, location of HOD room, location of staff room, location of classrooms, it is known as the placement. Okay, so routing means giving the connections between them. Okay, so between the connections between the different departments, connections between the different classrooms. Okay, so everything is taken as the routing. Okay, so if we, after that, once again we have to go for the circuit extraction. So here we have to remove the unwanted parasitics. Next again we have to go for the post layout simulation. So if you see here, from the design entry to the system part, from the design entry to the system partitioning here. Okay, so we may call it as the logical design. From the floor planning to routing, so we will name it as the physical design here. Okay, so this is about the ASIC design flow. So the next important one is the FPGA design flow. So in the FPGA design flow also, the design entry is the first step here. So the during the design entry, so you will create different source files using the hardware description languages such as HDL and Verilog. So after that, next we have to go for the simulation, behavioral simulation. So that means nothing but the checking of the behavior of your circuit. If this functionality, the functionality of the circuit is correct only, then we have to go for the synthesis. Okay. So as I told you, the synthesis is nothing but the generation of the netlist. Okay. So after the design entry and the optimal simulation, we run synthesis. So during this step, so which VHDL or Verilog designs become netlist files that are accepted as the input to the implementation steps. Okay. So the next one is nothing but the implementation. So after the synthesis, you run the design implementation. So this implementation will convert the logic design into a physical file format. Okay. So what the implementation will do is, the implementation will convert the logic design file. So that is the netlist into a physical file format. Okay, so this physical file format can be downloaded onto the target, so downloaded onto the FPGA IC. Okay, so now at this implementation time, you can also go for the static timing analysis. So what is meant by the static timing analysis? So far we have seen whether your circuit is functionally correct or not. So but we have not checked whether your design is correct in terms of the timing. Okay, so for example, if you are designing some circuit, some digital circuit, and I want to use that digital circuit at in some application. Okay, so that application will be running at a particular speed. Okay, so we have to check the compatibility of that also. So that compatibility will be checked by the static timing analysis. So there are two types of analysis. One is dynamic timing analysis, and next one is the static timing analysis. So in case of the dynamic timing analysis, we will give the inputs and we will check the timing analysis. So in the static timing analysis, we will not give the any inputs, and we will here find out the critical slack time. Okay, so again the topic will be very different regarding the static timing analysis. If the slack time in the static timing analysis is positive, means the device and the design what you are using will be compatible. So otherwise, the design and the device will not be compatible if you are getting the slack time as the negative. Okay, so yeah, the static timing analysis is very important part in the designing. Okay, so there are so many number of jobs on the static timing analysis. Okay, so after that after the this, so next we have to the implementation process here. So the implementation process will be varying from one target field to another target field. Okay, so if I am talking about the FPGA, means there are different companies that manufacture FPGAs. So normally FPGA means what you get into mind is Xilinx. Okay, so before that, whatever the flows which we have seen so far, all these flows, and at each and every step there are different softwares. You cannot do it with your hand. So there are different softwares. Normally in the academics, what you will do is that, so if you are going for the simulation, means normally you go for the Xilinx ISC, okay, or Vivado. So but these are not the prescribed tools. In order to go for the simulation, functional verification or simulation, means for the digital point of view, you got model sim, Vesta sim. So there are some tools that are only dedicated for the simulation purpose. Okay, so normal what you will do in the simulation is that in our academics, so you will give the, so after designing the program, so what you do means you will check the syntax. Once the syntax is correct, so you will open the waveform. So in the waveform, you will force the input values and we will see the output values. Okay, so but it is not the case. So if you are taking in the industry point of view, so what happens is that, so for example, if you take a what you call a full adder. So if you take a full adder, so for a full adder there are three inputs. A, B, C are the three inputs for a full adder. So if you want to verify the functionality of the full adder, so you have to give the 2 to the power of 3, that is 8 input patterns we have to give from 0 to 7, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, like that. So 0 to 7 we have to give the 8 input patterns. Okay, but in case of real time, if you want to verify the code, for example, there are some 2000 inputs in your code. So then 2 to the power of 2000. So you cannot imagine. So if you want to do every input, means the some 1 year or 2 years it will take. So you cannot force it. So for this there are different simulation techniques. So assertion based verification, like that. Okay, so assertion is the most important technique nowadays we are using in the industry. That is the assertion based verification for the verification of our circuits. Okay, so this type of techniques are not supported by the Xilinx or else. So we have to use the specific simulators. Okay, so these are only designed for that purpose, for the purpose of simulation. Here if you take, so coming to the FPGA, so there are different companies that manufacture the FPGA. Like Xilinx is the leading company that will manufacture the FPGA. So and after that, Ultra, okay, is one more company. So Lattice, QuickLogic, okay. So all these are the different companies, okay, that will manufacture the FPGAs. Approximately there are 20 companies in the world that will manufacture the FPGA. So but writing of the program, Okay, so after that simulation, up to simulation, you can do the in any software. Okay, but remember, in FPGA, from the point of synthesis, from synthesis to the implementation, so you have to use the vendor dependent software. For example, if I am dumping my code on the Xilinx FPGA means, so from the synthesis point to the implementation, so I have to use the only Xilinx company compatible software only, that is the Xilinx ISC or Xilinx Vivado. So for example, I am using the Ultra FPGA board means, so I have to use the Quartus software. So this Quartus software is provided by the Ultra company. So from synthesis to the implementation. So why? Because if you see the FPGAs, the FPGA is different. The architecture of lattice FPGA is different. So the FPGA's internal architectures will differ from company to company. So that is from manufacturer to manufacturer. So therefore, you cannot use the same software for all FPGA boards. So from synthesis to the implementation, we have to use the vendor dependent software only. Okay. So next, verification. So you can verify the functionality of your design at the several points in the design flow. So using the simulator software to verify the functionality and the timing of your design, we can see it. And next, after that, so we have to configure the device, the hardware device what you are using. So after configuring the hardware device, so you generate the configuration files and download the program onto the FPGA by using the given software. So after dumping your program onto the FPGA, so this FPGA board has different hardware resources. For example, if you want for the basic thing to see is, for example, if I want to give the inputs for your adder, and if you want to see the outputs means, there will be the set of pins on the FPGA board, and you can on or off that switches. And similarly, basic by changing the input pins, so you can see the LEDs on and off on your FPGA. So that is the LEDs on and off will show you how your output is working. So if the LED is off means the particular output is 0. If the LED is on means that particular output is 1. So like this, you can verify the any program on the FPGA board. So if the particular digital design is correct on the FPGA means, then you can go for the real-time implementation. So this is what about the FPGA flow. So these are the major flows. So VLSI design flow, ASIC design flow, on the FPGA design flow. So if you have any doubts, you can ask me. Hello, Suresh.
Hello, sir.
Suresh.
These
These are the flows for today. So from tomorrow onwards, so I can go into the Verilog design.
Okay, sir. Okay, students, you have any, the participation, you have any doubts, please ask me.
Sir, no doubt, sir. But teach us a bit slowly, sir. It seems to be very fast.
Okay. Tomorrow we will rectify our problems, okay?
Yeah.
Okay, sir.
Tomorrow
Okay.
onwards, so I
Thank
will be using the apart from the PPT, I will be using the digital screen in order to explain some syntaxes as well as some programs. Okay. So digital screen also will be
Okay,
used.
sir. Okay.
Okay. Yeah, thank you, sir.
Okay. Thank you, sir.
Yeah, thank you. Today's session is closed. Tomorrow, as it was 6 o'clock. 6 o'clock, we start this session. Okay, thank you, everyone.